Alright, so Chapter 11 really is all about using the mole ratio. And what the mole ratio allows us to do is to be able to go from moles of a product to moles of a reactant, and vice versa, or from moles of one reactant to another reactant. And that's helpful when we're trying to figure out, say, if we start with a certain amount of a reactant, how much of a product we can get. So in Chapter 10, we worked with moles and applied them to individual compounds. And now we're extending that to deal with equations as a whole. So moles allow us to move from one side of an equation to another and from one chemical to another. So the first set of problems in Chapter 11 all deal with this mole ratio. Question number 50 asks you to find what the mole ratio you would use to convert from moles of chromite, which is the FeCr2O4, to moles of ferrochrome, which is FeCr2. So you get the mole ratios by looking at your balanced chemical equation. And you use the coefficients from the equation to tell you what the mole ratio is. And so if you look at this equation here, what we have is we've got our chromite, right, with no real subscript, or coefficient before it, and ferrochrome, which has the same thing. When there's no coefficient before a compound, we can assume that that coefficient is 1. Provided that our equation is balanced, and this one comes to you already balanced. So what you can do is you can take these coefficients from the balanced equation and use that to make your mole ratio. So the mole ratio in this case is 1 mole of ferrochrome, to 1 mole of chromite. Basically, it means if you have 1 mole of chromite and you put it through a chemical reaction, you should be able to produce 1 mole of ferrochrome. Okay, number 61, you're basically building 50 here. So instead of just coming up with a mole ratio, you're asked, okay, if you have 5.50 moles of calcium carbide, how many moles of acetylene can you produce? So the first step here is to balance the chemical equation. And if you look at the balanced chemical equation, you get the mole ratio of 1 mole of acetylene to 1 mole of calcium carbide. And again, you get those numbers from the coefficients in the balanced equation. From here, it's just a matter of using this mole ratio to cancel out the units you don't want. In this case, you don't want moles of calcium carbide, and to leave you with the units you do want, moles of acetylene, C2H2. So providing your units work out here and you use the correct coefficients, you should be able to get the right answers. So you have your starting moles of calcium carbide, multiply it by the mole ratio to get moles of C2H2. Use the mole ratio to go from moles of one substance to moles of another. In 63, you add another step to this. So instead of going from moles of one substance to moles of another, now we want to take one more step and go from moles of a substance to grams of another. So we don't have a direct way to go from grams of one substance to grams of another substance, or from moles to grams. This needs to be done in multiple steps. So what this problem asks is in a process called esterification. You want to determine how much of this ethyl butanoate is produced if 4.5 moles of ethanol is used. They give you a balanced chemical equation. So you start off with your moles of ethanol. You got 4.5 moles of ethanol here. From here, you can go to moles of your ethyl butanoate or butanoate. I'm not sure of the pronunciation of it, but stick with me here. Okay, you can go from moles of one thing to moles of another using the mole ratio. So in this case, our first step is to get our moles of ethyl butanoate. Once we get our moles of our ethyl butanoate, we can use molar mass to go from moles to grams. So all we have to do is get to the moles of ethyl butanoate, and we can get grams there. So it's 2 steps. Use the mole ratio to cancel out your moles of ethanol, and then use your molar mass of ethyl butanoate to cancel out the number of moles of ethyl butanoate, and you should have grams as your final answer. So if you set up your problem correctly, you should end up with 523 grams. In 67, we add yet another step. So 67 gives you another balanced chemical equation, and it asks how much methane in grams is needed to produce 50 grams of chloroform. Chloroform is CHCl3. So as I said earlier, you can use the mole ratio to go to a balanced chemical reaction. It doesn't matter if you're going from one reactant to another reactant, or from a reactant to a product, or back from a product to a reactant, as in this case. You can still use the mole ratios given to you in the equation. So first here we're going to figure out what we start with. We're starting grams of chloroform. We need to go all the way to grams of methane. So this is going to take multiple steps, again, because that balanced equation doesn't give us a direct way to go from grams to grams. So if we think about what we need to do here, let's say we start with grams of one substance. From here we're going to need to go to moles of that substance so we can use our mole ratio. Once you've got your mole ratio, you can go to grams of your other substance, moles of your other substance, and from there to grams of your final substance. Anytime you go from grams to moles, or moles to grams, you're going to use the molar mass. When you go from moles of one thing to moles of another thing, you use the mole ratio. And again, that's dictated by the balanced chemical equation. Once you know what steps you have to take, it just becomes a matter of arranging your conversion factors to cancel out the units you don't want and to yield the units you do want. So we're starting with grams of chloroform here. We want to cancel out our grams of chloroform and get moles of chloroform. We're using the molar mass to do that, so we want grams in the denominator. We're going to divide by molar mass in our first step. So that's our first step checked off. We now have moles of chloroform. If we stopped at this step, that's what we'd have. From here, we want to use our mole ratio to get us from moles of chloroform to moles of methane. In our balance reaction, that ratio gives us our balance reaction gives us a ratio of 1 to 1. So in this case, we want to cancel out moles of chloroform, get moles of methane. Step 2, done. In our final step, we want to end up with grams of methane. So we look at our molar mass of methane. We want grams at the top. Our molar mass is 16.04 grams. We're going to cancel out moles. If you arrange everything properly, you should end up with 6.72 grams of methane. Number 69 is a very similar problem to number 67. One thing you're going to need to do in this problem is you're going to need to balance the equation first. So in this case, the book doesn't do that first step for you. So right here I've listed the balanced chemical equation for the reaction provided in number 69. You're then asked in number 69 to determine the mass of carbon dioxide produced from the combustion of 100 grams of ethanol. So what we're going to do is we're going to go from grams of our reactant to grams of our product. As we said before, we can't go directly from grams to grams, so we need to go from grams of our reactant to moles of our reactant, and then from moles of our reactant to moles of our product, and then from moles of our product to grams of our product. So you can follow the same steps as before, right? We use the molar mass to cancel out grams of our reactant. We use the mole ratio to cancel out moles of our reactant and get moles of our product. In this case, that mole ratio is 2 to 1. After you get moles of your product, you use the molar mass of your product to get grams of your product. And you end up with 191.1 grams of carbon dioxide being produced from this reaction.